minutes and 5 minutes for questions. After 20 minutes, I will let you know. Okay, let's start.
Okay, can you see my screen? Can you hear me?
Yeah, we can see your screen.
Okay. Okay, can I start?
Yes, yes.
Okay. All right. So yeah, thank you very much for the organizers for giving me this opportunity to present the project Hyperkamiokande in this conference. I'm Masashi Yokoyama from University of Tokyo. So yeah, we have a really good news this year that actually the Hyperkamiokande was approved from the Japanese government. So this is an announcement from the University of Tokyo, the host and KK, host of the Hyperkamiokande project. And right side is that unfortunately this is Japanese, but material explaining budget for the large-scale science project in Japan from the MEXT, our funding agency is the government. So this year, as a new project, they feature this Hyperkamiokande. So the construction work, some of the construction work has already started from early this year, and we are planning to start operation of this Hyperkamiokande from 2027. So the Hyperkamiokande is actually the third generation of the Kamiokande experiment series. So actually, by the way, Kamioka is the name of the place where the detector is located. And Nde is that originally a nucleon decay experiment when Professor Koshiba constructed this proposal and constructed this original Kamiokande detector. But actually, he couldn't find the proton decay, but he succeeded to observe neutrinos from the supernova in 1987 and got Nobel Prize in 2002. So so it's now called Nde, also stands for the neutrino detection experiment. And the second generation Super Kamiokande detector is, as you know, used for the first observation of the neutrino oscillation via atomistic neutrino. And Professor Kajita was awarded the Nobel Prize in 2015. 5 years ago. And now we started constructing even larger detector, Hyperkamiokande, as based on the huge success of these two Kamiokande and the Super Kamiokande detectors. So those detectors are large underground water Cherenkov detector. So we observe and measure the high energy charged particle via Cherenkov light. Those particles emit in the pure water, and detect those lights via using the large, many larger photomultiplier tubes located in the detector walls. So we can observe clear Cherenkov rings, and from the pattern on the intensity and the charge and timing distribution of these Cherenkov rings, we can measure the energy, direction, and interaction vertex of the particles. And also it's important to distinguish muons and electrons, especially for the neutrino oscillation measurements, to identify the flavor of the interacting neutrino. And we can achieve the less than 1% misidentification probability for the EMU separation using the by the pattern of these Cherenkov rings. And it has a 4-pi uniform coverage with real-time information. And also, water Cherenkov detectors can cover very wide energy range. For example, in the case of Super Kamiokande, we can observe down to 3 MeV solar neutrino to the 100 GeV or even TeV range using the surrounding rock as an interaction target for the atmospheric neutrinos. So with this wide energy range coverage, we can do really many physics measurements. And because of its rather simple structure, design of the detector, it's scalable to large mass, and it's a very established technology over the more than 30 years is Kamiokande and Super Kamiokande. So currently, Super Kamiokande detector is running since 1996, and as I said, that in our first few years, it brought the discovery of the atmospheric neutrino oscillation. And after that, amazingly, over more than 20 years, Super Kamiokande has been providing world-leading discoveries in the mostly related to the neutrino physics and astrophysics. And it's actually still evolving. So yeah, 2 years ago, we had some major refurbishment work inside the detector tank. And this is a proof photo that I worked with. And we had also many colleagues from outside of Japan, including Russia, for this massive work. And this is in preparation for the upgrade and to dissolve a small amount of gadolinium in the water of the Super Kamiokande tank. And now to enhance the neutron tagging capability, detecting gamma rays from the neutron capture on the gadolinium. So now this summer, we dissolved a smaller amount. It's 13 ton, but compared to the 50 kiloton of water, it's a very small amount, but of the gadolinium. And it gives us about 50% of the neutron capture efficiency. And which will enable us to do rich physics program, including the observation of related supernova neutrinos. So yes, this shows that really capability can be extended even after more than 20 years of the operation, and demonstrates a great potential of this kind of water Cherenkov detector. So now, we are still upgrading the Super Kamiokande, but in addition to that, we are going to build even larger detector, Hyper Kamiokande, as a next generation detector. So Hyper Kamiokande project consists of mainly two parts. One is the main detector, Hyper Kamiokande, that will be hosted by the University of Tokyo, which I belong to. And the other part is that JPAC, that's the hyperproton beams, and provides hyperproton synchrotron facility that will provide neutrino beams for the long baseline neutron oscillation experiment, and also the near and intermediate detector system that will be hosted by the KK, our high energy physics laboratory in Japan. So combining this large, huge, and capable detector and intense and precise beam with measurement near detectors, we will do the long baseline experiment and also the non-accelerator physics experiments or observation in a single project. So HyperK will cover a very wide range of science program from the neutron oscillation physics, of course, with a neutron beam and also atmospheric and solar neutrinos, and search for nucleon decay towards that possible discovery of the evidence of grand unification theory, and also the neutron astrophysics using the solar neutrino and the supernova neutrinos. And even we have some program for the geophysics, looking at interior of the Earth using the neutrino, utilizing neutron oscillation. And maybe we can think of more subjects and may discover unexpected phenomena. So as I said earlier, the detector can cover a wide range of the energy as a measurement target, and a wide range of the science can be covered by the HyperK. So the hyperchemical detector will be built in the actually different mountain from the where Super K is located now, and it's around about 8 kilometers south of the Super Kamiokan, still in the Kamioka town. And the tank, water tank will be 68-meter diameter and 71-meter height. And this is a comparison of the cavern size of the Super K in red and Hyper K in orange. And this is that Hyper K is huge, even compared to the Super Kamiokan. So, but so this large detector is of course necessary to increase the statistics and for the precise measurements. But hyperkamiokan is not just a larger version of the super kamiokan, and we are trying to improve the performance in every aspect of the detector. And one of the key components is of course the PMT. So we newly developed a new PMT for the hyperkamiokan together with Hamamatsu, and this is a 50 centimeter diameter PMT. But dynode structure is improved, and also the many bulb shape or glass material, all parts are improved, and we actually have that factor 2 better detection efficiency compared to the super kamiokan, the PMT, and also that factor 2 beta charge resolution and timing resolution. These are real measurement of the more than 100 PMTs, new PMTs installed in the super kamiokan during this refurbishment work 2 years ago. So we are pretty sure that this is improved in the real water Cherenkov detector environment, and also it has a twice better pressure tolerance, so that enables us to design a taller tank and optimize the design, and also while improving efficiency, dark rate is kept low, and outer contamination is kept low, so that the background for the low energy measurement is also suppressed. So with this kind of improvement in the PMT, we can improve actually the science. So I would like to explain one example: proton decay search in the Nuba K mode, and K plus decays to the muon plus neutrino. And this is one of the proton decay mode favored by Suji GAT, proton decays to the new bar anti-neutron and kaon. But unfortunately, this kaon from proton decay is momentum is below Cherenkov threshold, so we cannot directly see this kaon in a water Cherenkov detector. But instead, we identify this by this monochromatic muons from the as a decay daughter of K plus, and with its decay electron. But just muon, just by detecting muon, we have a huge background from the atmospheric neutron interaction. So in order to reject background, we utilize this de-excitation gamma ray from the nuclear de-excitation when proton inside oxygen decays. So identifying this, this is a Monte Carlo distribution of the number of PMT hits as a function of timing. So in addition, so we can see that the muon, the decay electron signal, and this small peak here is a gamma ray from the nuclear de-excitation. And this gamma ray and muon signal is separated by the kaon lifetime, that's 12 nanosecond. So by improving PMT timing resolution, we can have better separation with this gamma ray and muon. And also the better photon detection efficiency will help to identify this tiny gamma ray signal. So Actually, by improving the PMT performance, both in the efficiency and timing, we expect that better efficiency of this proton decay search in the hyper-K compared to the super-K. So this kind of the proton decay search is, of course, one of the major goals, subject of the hypercameo-Kande. So if we can find this will be direct evidence of the ground unification theory. So two modes are often used as a benchmark, E plus pi 0 and nu by K plus. And of course, that other possible modes are also important. So we will search as many decay modes as possible, like we are just doing in super Kamiokande already. But by hypercameo-Kande, we can extend the sensitivity by basically one order of magnitude. So this is a sensitivity curve as a function of time for the proton goes to E plus pi 0. This is not a 90% confidence level limit, but 3 sigma sensitivity, because we want to really discover this decays. And if a proton lifetime is near the current limit, we would see this nice proton mass peak in the invariant mass distribution over almost negligible background from the atmospheric neutrino. And those right side plot is at similar sensitivity as a function of time for the nu by K mode, and the hyper K will have a world-leading sensitivity. As a comparison, Juno and Dune sensitivities are plotted, and hyper K will provide the world-leading sensitivity for the proton decay. And of course, that another important topic is the neutrino oscillation measurements. And already in this conference, there are several talks about neutrino oscillation. And we have many questions about new properties of neutrinos and also the physics behind that. So the origin of tiny mass or emission parameters, mass ordering, and CP violations. So in the hyper-K, one of the major topic in the neutrino oscillation is, of course, a CP asymmetry measurement, or search for the CP violation in the neutrino oscillation. So I think that yesterday Nakaya-san gave a plenary talk on this long baseline neutrino oscillation measurements, and CP violation can be proved by comparing probability of neutrino oscillation in the nu mu to nu e versus nu mu bar to nu e bar. And already T2K and NOVA started as a measurement of those oscillation probabilities. And as reported yesterday, T2K reports a hint of the CP asymmetry, but there's some tension with what NOVA reported this year. So we should continue definitely to study this. And currently, the number of candidates summing, adding both a nu e and a nu e bar is around 100, just 100 for the both of T2K and NOVA. So of course, that both experiments plan to collect more data, and also the combined analysis of the T2K and NOVA is ongoing. But in future, the hypercameo-Kande will detect around 2,000 new candidates for each of the nu e and nu e bar. And we expect a definite measurement of the CP asymmetry. So this is expected significance of the CP violation as a function of that depending on the true value of the CP phase, delta CP. So we will have that more than 5 sigma significance over more than half of the parameter space. And also we will see that 10,000 events for the nu mu and nu bar. And actually, mu neutrinos are almost oscillated, so number of events is decreased due to the oscillation. But anyway, with those large number of events, we will precisely measure the oscillation parameters, and we can do the consistency check with other measurements like reactor experiments or different baseline energy long baseline experiments like NOVA and DUNE.
Okay. Excuse me, 5 minutes left.
Oh, okay. So for this neutrino oscillation measurements, long baseline experiment is a measure way. So the power of the neutrino beam is a key for this measurement and statistics. So in JPAC, we are doing some power upgrade. So by shortening the repetition cycle from current 2.5 seconds to almost 1 second, and also loading more protons per pass on the beam. And also, in addition, the neutron beam line will be upgraded to handle the high power beam. So we expect 1.3 megawatt compared to the current 100 kilowatt in the era of the around when Hyper-K starts operation. And this upgrade will be done together with the operation for the T2K experiment. And also, in addition to the increase of the statistics, control of systematics is very important. So we will utilize near and intermediate detectors. So we are currently measuring neutrinos with the near detector in T2K, and this alpha-axis detector will be upgraded in a couple of years. And this is we had a talk on the Super FGD this morning, I think. This is developing INR, and maybe we will have a further upgrade for Hyper-K. And we are proposing water Cherenkov detector as an intermediate detector with a 1 kilometer baseline. And this detector can move vertically so that it can sample different flux angle and different neutron energy. So this will give another handle to reduce the systematic uncertainty. And other than the neutrino oscillation measurements, we have a broad program of the neutron astrophysics. So its unique role in the multi-messenger observation by detecting solar neutrinos and the supernova burst neutrinos and the supernova relic neutrinos. And even we have even more science topics like indirect dark matter search, and even that neutrino oscillogram of the Earth core. So some geoscience, some collaborators working on the geoscience. So using the remaining few minutes, I will just briefly explain the status of the project. So as I said at the beginning, the construction has started. So we are in Kamioka underground. We are now doing the detailed geological survey of the candidate site. And actually this survey tunnel reached around the center of the Hyper-Kamioka and the tank top region. And we are preparing also the entrance of the access tunnel in preparation for the heavy construction that will start in the 1 year or 2. And based on those survey information, we are going to have detailed design of tunnel and the cavern. And also this year we start production of the PMTs. And in the JPAC site, we are the upgrade of the power supply of the accelerator, and also the upgrade of neutron beam line is ongoing. And also we are investigating the near and intermediate detectors design. And so the project will be hosted by 2 institutions, University of Tokyo and KK. And after the approval of the project, those 2 institutions signed an MOU to promote Hyper-K project in May. This is the president of the University of Tokyo and the director general of the KK signing the MOU. And we defined that project management organization within the host institutions jointly. And we already had the first meeting of the PSC last month, and other organizations are also being formed. And the collaboration is, from since 5 years ago, we had a proto collaboration, but now after this approval, we are transitioning to the full collaboration. So we established the collaboration agreement and formed institutional board and selected its chair. And we are now doing the election of spokespersons and so on, and defining working group and leaders for the construction. So now we have the around 430 collaborators from 19 countries, and these numbers increased compared to 1 year ago, and still growing. So yeah, we welcome new participants to the HyperK project. So with this collaboration, we have international effort for the HyperK construction. So various R&D or is ongoing for the construction and production. And this is a project timeline. So we started project from this year, 2020, and after design, excavation, and the production of the many detector parts, we plan to start the operation from 2027. So yeah, this is the conclusion. So HyperK Myokande will be the next generation water chemical detector, and with a broad science capability, broad and excellent science capabilities. And the project was approved this year, and the construction has started. So we are working for the start of the experiment in 2027. Okay, that's all.
Thank you very much. We have 3 minutes for questions. So 1 or 2 questions, short questions, please.
Well, hello?
Yes, please.
Hello? I would like to ask the question, maybe not related to science, but I'm so deeply impressed by the dimensions of the chamber. So I'm curious about how you understand this. This is to excavate so big chamber and to support the vault, for example. It's something absolutely new for even for you in Japan, or you have some previous experience in excavating so huge caves.
So right, so yeah, as you correctly pointed out, this excavation of this huge cavern is not trivial, of course. And so we have several large-scale caverns in Japan, and we, of course, that we have been consulting the large construction company to design this cavern, and we already did several boring and geological survey of the candidate site. And confirm that of course that we have detailed design of how bolt should be located to support this cavern and so on. And we are pretty confident that that can be built with current technology. But talking about the size, this will be I believe that this will be the largest underground cavern in Japan. Its size, so it's strange, but we are confident that we can build this.
More questions? If nobody have questions, may I ask you shortly, what can you say about building and construction the similar detector in South Korea?
South Korea. Right. So yeah, there is some as you know that there is some proposal basically from the Korean colleagues to design and build the similar. Actually, it was originally proposed as the second detector of this HyperK project and in Korea, so that we have a different baseline of this long baseline experiment. So now I believe that Korean physicists are investigating the possibility, like survey of the candidate site and designing more technical design of the detector, and also the physics capability studies. So I heard that they got some small money for this feasibility study from Korean government, but yeah, still they are in the some early design stage, I think. And we are working. We have been working together. And, yeah.
Okay, thank you very much. If no questions, well, actually we don't have time for more questions. Let's go to the next talk. Evgeny Yakushev from Dubna, new millikelvin temperature germanium detectors for dark matter direct search and for precision measurements of sevens. Please, 25 minutes for talk and 5 minutes for questions.
Hello, everyone. My talk will be about new millikelvin temperature germanium detectors dedicated for dark matter direct search and for precision measurements of coherent scattering of neutrinos. So this talk is related to two experiments, Edelweiss and Ricochet. These two experiments are connected, as you will see from my talk. So I want to start. Sorry, somehow it doesn't work. Okay, sorry. So I want to start my talk from this slide. Thanks to organizer of this conference, we see that dark matter and neutrinos are two topics between hottest topics of the particle physics and astroparticle physics. And the reason for this is very obvious. For neutrinos, this is most abundant massive particle in the universe, and for dark matter, dark matter particles, they are most massive part of the universe if we speak about particle. So of course, this is the reason why there is many experimental way how we try to study both these problems. So now if we speak about dark matter, then one of the possibility to study it is to try to detect scattering of dark matter particles inside of the particle detector in the laboratory. For example, in germanium crystal, if a germanium crystal equipped with electrodes and we apply a field, then we can collect results of such scattering, that means ionization. And if we have a thermistor attached to the germanium crystal, then we can also detect phonons, means heating of detector as a result of this of such scattering. So this method is used in the Edelweiss experiment that use germanium bolometers for detection of dark matter. And of course, the experiment has to use all classical methods for background reduction in the way to detect, try to detect these dark matter particles. So detectors are running in very deep underground laboratory. This is Laboratoire Souterrain de Madan in France. It has 4,800 meters of water equivalent overburden. Then, of course, we have to run experiments in a clean room, have very clean air, clean from radon. We have still, even inside of the deep underground laboratory, we have to use active muon vector. We have to use a very massive different kind of shields against gamma radiation, against neutrons. And of course, all materials have to be selected in advance for their radio purity. So you can see here how this implemented in Edelweiss. So you can see inside there is a cryostat with germanium detectors. As we are measuring both ionization and heat, so for phonon signals, detectors has to run in very low temperature. So this temperature is below 20 millikelvins, and for to be so cold, we have to use helium-3, helium-4 dilution cryostat, where we can put about up to 50 kilograms of detectors and make temperature below 20 millikelvins. So, but why we need to measure both ionization and heat? If usually for germanium detectors, you know that we can measure just ionization and they work just fine. This is because traditional methods for background reduction are not enough anymore for search of dark matter, as its interaction with normal matter is a very, very random event. So if is using both heat ionization, we can distinguish between events produced by nuclear recoil. This means, for example, recoil of weakly interactive massive particles on germanium nuclei, and between ionization that can be produced by gamma radiation. Gamma radiation is one of the most dangerous background in all its rare events experiment, as it has huge penetration power. All elements on Earth has radioactive contaminations from natural radioactive elements, uranium, thorium, potassium, etc. So this is this is what we have to eliminate in order to be sensitive to very, very random events of dark matter collision with normal matter. So in either device, with using these heat ionization detectors, we can say if it was a nuclear recoil or if it was electron recoil, as you can see from this spectrum on the right. So with using of americium beryllium neutron source that also produce gammas, of course. So we can see two bands. One is, and this is a plot of ionization yield to recoil energy, and recoil energy we know from measurements of the phonon signal, because heating of detectors correspond to full energy deposited inside of the germanium crystal. And so in this way, we can separate about 99.99% of all gamma radiations from nuclear recoils. But it came out that this is not all story. So this is not enough to be sensitive to dark matter on the modern level. So next step was that was introduced to our detectors is this special scheme of electrodes on our detectors, so-called fiducial interdigitized scheme for charge collection. And you can see here how it works. So if events is happen in the bulk of our detector, then it sort of see electrodes on both sides of detectors and charge collected on the opposite sides. And if events is happen near the surface, then charge will be collected on the neighbor electrodes. Why we need this? This is because on surface we can have some trace contamination from radon daughters, for example, or from carbon-14, and this contamination, when it's during the decay, product of decay, so when pass some layer on surface of detector, it lose some charge in this layer and this in the electrodes, and this we cannot collect by electrodes. So in this case, we have events with miscollected charge, and this can mimic events of nuclear recoils. This is why this complicated schema was introduced to our detectors. And with this schema, we were able to go to very, very low background to search for dark matter candidates. So in general speaking, for 25 years, Edelweiss is developing different techniques for dark matter detection with germanium detectors. And if we speak about very recent developments, let's say last 5 years, I can say that these germanium detectors are not competitive anymore with huge argon-oxenon-based detector that they are running many tons of materials, and of course producing such detector with germanium on them these days is still very complicated. So our program was shifted to a region of low energy, where inaccessible by this huge detector, argon-oxenon. So in the same time, there is increasing gain of interest for search of low mass or very heavy WIMPs and other possible candidates for dark matter. Why it's like this? One of the reasons, there is several reasons. One, if you look on this plot on the right, this is produced by Xenon collaboration last year. That I think this was one of the last results for WIM search. So you can see that they already have this very, very impressive sensitivity in the region of 10⁻46 centimeter square for WIMP mass, for this traditional WIMP mass in the region around 100 GeV. So they accumulated more than 1 ton year of data, and they see no events of dark matter. So in the same time, there are no evidence yet for supersymmetry at LHC. And as you remember, the supersymmetry particles were considered as one of the main natural candidates for dark matter. In the same time, of course, there is many new theoretical approaches that predicted lighter candidates. So in the same time, there is also some controversial results in the low energy region. Of course, many of these controversial results are connected with not well understand background in the region, but in the same time, it could be that there is something interesting. For example, I will show you this plot also produced by Xenon collaboration just about 2 months ago. You can see they also observed some events in very low energy region, and they explain this. One of the explanations of this is interaction of axions in their detector. So this axions is also between these light candidates for dark matter. So this means that this region has to be investigated. So in the same time, all experiments, as the sensitivity of dark matter experiments improving, they are approaching of so-called neutrino floor. So at some point, coherent scattering of neutrinos will become background for all dark matter experiments. You can see here this region for low energy starting in 10⁻44, and for high energy is 10⁻48, 49 centimeter square, where this will be unavoidable background for all dark matter experiments. So immediately there is interest from one point of view to try to reach sensitivity in dark matter experiments to this level. So start to study neutrinos, solar neutrinos, for example, with this new channel. And in the same time, this means that this cross-section for coherent scattering of neutrino on, for example, on germanium become extremely important for future of dark matter search experiments, because their interpretation will depend on how well we know this cross-section. So to move to low threshold, low energy, dark matter particles, we have to reduce threshold. This is the way how we can access this energy region. So now, if we speak about Edelweiss experiment, there is 2 modes how we try to reach this low energy region. One is this usual approach when we use this previously developed heat ionization bolometers, and just to try to optimize them in the way that they work better. This means they have better energy resolution, low noise, better discrimination between signals and different kinds of noises. And we try to reduce backgrounds, of course. And second option is high voltage options. So this high voltage options is connected with internal amplification of heat signals thanks to Neganov-Trofimov loop effect. So what is this effect? This effect is very simple. When we apply a electric field to collect charges inside of our crystals, and when we collect these charges, we produce work. This means that we are additionally heating our detectors. So this means that more bias we will apply to electrodes, more amplification of the heat signal will be happening inside of our detectors. So in this way, we can really change by internal amplification. We can gain a lot as we are moving real events from the noise that we have in our detectors. So for example, here you can see on this plot how calibration spectrum with barium 133 source changed in case when we apply different voltages for our electrodes in one of the detector. So first we have a usual voltage, 8 volts, and then we move to 100 volts. And you see that it's change, the position of the line change significantly. In the same time, you can see how resolution of the detector changed when we apply different voltage. At 8 volts, we had quite poor energy resolution, more than 500 electron volts, and with 100 volt bias, we had energy resolution below 50 electron volts. So this is very impressive. Of course, for example, to put this high voltage, this scheme of electrodes on the detector has to be changed because we need more spacing between electrodes, as two near electrodes will produce crosstalk and nothing will be possible to measure. Of course, we have to implement a number of other changes in scheme of our measurements. I have no time to talk about. I will say that different type of detectors were produced by Edelweiss, and they all were first tested on surface, and then we start to test them in underground lab. So we did a relatively long run from January 2019 to June 2020. And we had 11 different germanium detectors equipped with different thermal sensors and designed with different supports. And we were able to reach really impressive results. You can see here experimental spectra with these detectors on the right. You can clearly see these cosmogenic lines in germanium down to M lines. That is 160 electron volts. Of course, when you use this Neganov-Trofimov-Luke effect, there is always price to pay. So of course, you are losing in discrimination between events. You increase voltage, so you are shift your events from noise, but in the same times you are losing discrimination between nuclear recoils and electron recoils. But you start to see events with very, very low energy. So with using these detectors, this is very preliminary results. You can see experimental spectrum that we were able to accumulate during several months. And you can see that we were able to measure starting from below 1 electron hole pairs events. So this is very, very low energy, below 3 electron volts. And with this, with using some models, some theoretical prediction, we were able to set some limits on dark matter particles. I will not speak a lot about this. You can find this in the paper. So now about neutrino, second branch of experiment. So at once we were able, about 3 years ago, to produce these detectors that were able to measure with very low energy threshold. Immediately we start to think how to implement them to investigate neutrinos, and then this new scientific program named Ricochet is appeared. So Ricochet aims at building ultra low energy 7th neutrino observatory dedicated to physics beyond the standard model. So we want to use same technology developed in Edelweiss with a huge background rejection possibility, and to apply it for measurements of neutrinos. So why we need these bolometric techniques? One of the reasons is probably will be clear from this picture. This picture demonstrates quenching in germanium detectors in low energy region. As you can see, there is huge uncertainty about quenching. That's more than 10%, I will say. And this means that with traditional germanium detectors, no one will be able to reach huge precision in measurements of coherent neutrino scattering. And bolometric techniques, when we measure energy deposition from nuclei directly by phonon signal, this became possible. So of course we will need some shieldings, etc. And of course, we will need a neutrino source. So here is the expectation of spectrum in standard model from different neutrino sources. So we consider it a nuclear power plant, 15 meters from the core of, for example, Kalinin nuclear power plant. Then scientific reactor in Grenoble, ILL, at 8 meters from the reactor core. And then in the double shoe, 400 meters from double shoe reactors. So this is this red line. And black dots is the spectrum on surface with the same detector. As you can see, in fact, even with very moderate shield on surface, we are not so far from strongest signal expected at, for example, in commercial reactor. Of course, if we speak LL reactor, we need a quite good shield against different radiation to be able to detect neutrino signal. So now,
excuse me, 5 minutes left.
Yeah, okay. So now, if we speak about precision, yesterday we had really good talk from Yuri Yefremenko, who explained very well why we need to measure coherent scattering. And one very important point is this electroweak angle or Weinberg angle, how we call it. So you know, this is one of the main parameters of standard model. And so far, it's not defined very well. Actually, we don't know why this angle has also this value, about 0.25. But if you look on the cross section for coherent scattering, you will immediately note that there is two parameters. Then it's this parameter is you have to square it. And usually, because this is sinus of this square of this angle is 0.25, so then you have no influence of charge of your nuclear on cross section, only number of neutrons squared. But if small difference of this sinus square from this value exists, then it's become very sensitive. This cross section is this means number of events detected from coherent scattering became very sensitive to this angle. So, for example, I will show here. This is what we can reach in measurements at ILL reactor with this 1 kilogram of Edelweiss style detectors. And you can see for exposition, relatively short exposition, if we have a good precision and a low background, precision measurements in about a few months of measurements. So as I already said, there are 3 sites we considered. And now this site for first phase of the measurements is ILL reactor in Grenoble. This is 58 megawatt thermal power reactor. And from this reactor, we expect about 20 events per day per kilogram of detectors in the ricochet detector. And proposal to use this reactor for these measurements was submitted in February, and just 10 days ago it was approved with additional money from ILL for installation. So there is some special advantages to use ILL reactor for ricochet experiment. And one of the most important is that we will take the place that is now taken by stereo experiment. So we will know background from the stereo experiment because they provide all data they accumulated during many years of running near the reactor. So we know about neutron background, we know about gamma background, we know about what signal to expect, neutrino signal to expect at this place. So here on this plot, I show you 7th discovery significance with 1 kilogram of ricochet detectors. And you can see even after first cycle of reactors that has 50 days on and 50 days off, we already will have about 30 sigmas of significance of the signal. So now this is almost last slide when I will speak a little bit more about precision. And I will concentrate on this low table. And you can note from this table, there is a main uncertainty is coming actually from fission spectra that is not known so well. So then another uncertainty is coming from that is of course, one will ask about backgrounds. So what backgrounds we expect? As we know very well, estimation of it from stereo. And for electron recoils, in total, we expect about 100 after using of a different kind of shield. But then with a huge discrimination power, this will be reduced to negligible value below 1 counts per day. And for neutron recoils, we expect about 5 events. And with 20 events of coherent neutrino scattering signals, of course, we will have very good ratio of signal to background. So this will provide us possibility to do this precision measurements. And this is almost last slide. So of course, if you look on this slide with expected spectrum, one can note that if one can run in this commercial reactor, then you have huge gain in ratio of signal to background. And we started to study one of these places, and this is not by surprise Kalinin nuclear power plant, but a new place is Novovoronezh nuclear power plant, where we with Department of Safety of this plant performed some first measurements of backgrounds, and they are very promising. So we found the place about 20 meters from a reactor, very this has no noise, no vibrations, and about 50 meters of water equivalent, and with neutron background that is about 20 times less with respect to the sea level. So ricochet timeline is that we have very aggressive timeline, so we want to start deployment of the experiment at LL in 2022. And we want to deliver first results not later than 2025. And in the end, there is two main conclusions to my talk. One is maybe more philosophic, that in general, all modern methods of nuclear physics have to be applied to achieve the sensitivity levels that are interesting now for particle physics. And second is maybe more direct for my talk, and that direct measurements of energy deposition and the energy and excellent energy resolution provided by the bolometric techniques as a base for its future use for investigation of rare processes like dark matter or neutrino sector. Thank you very much.
Okay, thank you very much, Evgeny, for your nice talk. So we have time for a couple of questions.
May I ask a question?
Okay, yes, of course.
What is lifetime at the moment for bolometric technique, typical lifetime measurements?
What is lifetime?
Lifetime. So
Lifetime.
if to take, for example, during a year, how many days you are really counting and how many days you are just working with the technical problems with the cooling and so on?
Okay, so for example, for Edelweiss, Edelweiss is using let's say homemade cryostat, helium-3, helium-4 dilution cryostat. So this cryostat is required relatively long time for cooling, about 2 weeks from start. So first, of course, there is nitrogen filling, and then after some cooling down, there is gallium filling, and then after some time we start dilution, and after 2 weeks we are at 20 milli-K. So after that, about once per 2 weeks we have a helium refill, and it takes half a day. And then in this mode, if no any problem with pumping and things like that, then we can run for a long time. Like for last time, we ran more than 1 year. And for ricochet, I had no time to speak about this, but now we will use a different technique. This is now there are commercial cryostats dilution cryostats available, and we will buy one of these cryostats. Actually, we already had one of these cryostats for test at Leona, and where we did a different kind of R&Ds. And advantage of this cryostat is that it's not require any gallium filling. So it's collect all gallium during its works. So usually to start this cryostats, it's about 1 day. And after 1 day, you already can do measurements. And after that, you can continue these measurements as long as you wish. There is no any stops or special stops you need. Like for this new type of cryostat, you need for just about like 5 liters of liquid nitrogen per week. That's all.
Okay,
Right.
thank you.
Any more questions?
I have also a question, Zhenya.
Yes.
So how do you think if people have looked for a long time dark matter and never observed yet, but maybe there are obvious evidences for dark matter that we see every day in every physical setup? I mean beta and alpha decays. It's first evidence, and then maybe if you cool your setup, for example, to absolute zero, the movement of atoms in the net continue to be. Why? It's impossible. Instead, if you have collisions with dark matter.
Yes, I will not comment on this. I can only say that what we try to do, we try to detect interaction of dark matter particles now in very low energy region, already at 1 electron volt region, and to try to see if there is any signals. So if you speak about this usual decays, usual interaction and influence, of course, for example, if we have axions as dark matter, of course, there is influence of this axion scalar field to all interaction. One of these examples is this Hungarian boson that is now also like one of the very interesting candidates for dark matter. And of course, this is influenced directly on decay, so it can be produced for high energy decay of gallium.
I see. Okay, it was a rhetoric question, so I didn't expect the answer. Okay, thank you. So because I have a new view on this problem. Okay, but okay, thank you.
Okay, thank you very much for a very impressive talk. And so, do you have any more questions? Because we should interrupt now for break. Only one short question. No. If not, we should break for lunch. We should have break for lunch, so we come back in 1 hour at 15:30. The same conference room.
Okay, bye.
Bye.
Yes, we can.
Okay, thank you. Welcome to the after lunch part of the plenary session devoted to neutrino. And the next talk in this part is the talk by Dmitry Zaborov, High Energy Neutrino Astronomy and the Baikal GVD Neutrino Telescope. Please, 25 minutes, and after 20 minutes, I'll let you know. About 5 minutes left.
Right. So let me know if you can hear me well.
Yes, yes, please.
Yeah,
begin.
is that okay? Yeah. All right. Then good afternoon, everybody. I would like to thank the organizer for the opportunity to present this talk. The talk is of two parts. First is introduction to the neutrino astronomy. If you didn't attend yesterday's neutrino session, that may be useful, or simply if you're not familiar with the field. And the second part is a status report on the Baikal GVD experiment. Why use neutrinos for astronomy? There are actually many reasons for that. Neutrinos can escape from dense environments that are opaque to gamma rays or other wavelengths of photons. Neutrinos can traverse gas and dust. It does not interact with CMB or infrared background. It is stable, or at least we think it is stable, and it's not affected by magnetic deflection. And finally, it's a good messenger for studying non-thermal processes, such as those related to cosmic ray acceleration and production and acceleration. So in this talk, we are dealing with energy range from about 10 GeV and up. This is what we understand by neutrino telescope, is something working in this energy range. In this range, we are mainly dealing with atmospheric neutrinos and astrophysical neutrinos, which is a main topic for surges. So how does a neutrino telescope work? Traditionally, we are using Cherenkov technology. So a neutrino hits a nuclei somewhere in the detector or in front of the detector. This produces secondary particles which produce Cherenkov light, and we detect this Cherenkov light with photomultiplier tubes. And this, of course, needs to be done in transparent medium. And because we need a very large size, something like a cubic kilometer, we can only use naturally existing site. This is usually clean water or clean ice. So light produces hits in the PMTs, and you use these hits to reconstruct the event from hit positions and times to reconstruct the direction, and from the charge, how much light you see, you reconstruct the energy. This technique is sensitive to neutral current and charge current processes by all neutrino flavors. In case you have muon neutrino interactions through charge current, you get a long muon track, usually a few hundred meters or a few kilometers long. So this is an event topology which we call a track. And all other events, they are usually referred to as showers or cascades. So in the search for astrophysical neutrino, we have to deal with backgrounds, particular from atmospheric neutrinos. Atmospheric neutrino background is a 4 pi background, and it's almost irreducible, although there is some methods to get rid of this, thanks to the fact that neutrino comes, if you are looking for neutrino from above, then it's sometimes accompanied with an atmospheric muon bundle, because they actually come from the same initial interaction of the primary cosmic ray. So this can be used to veto atmospheric neutrinos. But normally this is a rather difficult to reduce background. Then we have to deal with atmospheric muons or muon bundles. These can only come from above because they cannot traverse the Earth. So you can get rid of them by reconstructing the track and making a cut on the zenith angle. And of course, you can have some environmental background light, which can also spoil somewhat your experience with measuring these events and limit your low energy sensitivity. Currently, there are 4 neutrino telescopes operating in this energy range around the world. First is IceCube, which was completed in 2010. It's about a cubic kilometer size. There are some plans to extend it to larger size using optic and also radio methods. Then in the Mediterranean Sea, there's Antares, which is actually a previous generation experiment relative to IceCube, but it's still operating. It's at least 50 times smaller than IceCube, and it was optimized for lower energies. Then there is KM3net, which is in fact 2 detectors. The one of interest for astrophysics primarily is called ARCA, and it's going to be about 1 cubic kilometer, similar to IceCube, and it's now under construction. So these use seawater. And there is also Baikal GVD, which will be the main part, the second part of my talk. It's going to be also a cubic kilometer big, and it's half complete, and I'll give you more details in this talk. So IceCube is, as I said, is a cubic kilometer detector. It consists of about 5,000 optical modules installed at depths between 1,500 and 2,500 meters in the ice, in transparent Antarctic ice. Besides the main array, there is also so-called deep core, which is an additional dense core mainly for neutrino oscillation studies. And there is also air shower detector on top of the ice. The detector was completed in 2010 and produced already many publications, discoveries, and so on. The energy threshold for these detectors is about 100 GeV for the main array, and it counts about 200 atmospheric neutrinos per day. So most results that exist in this field, they come from IceCube so far. So Antares, as I said, is a previous generation, and it has less than 1,000 optical modules. Has been in operation for 12 years, producing also many publications, unfortunately only upper limits on sources. So these had 12 strings, 25 stories per string, and 3 optical modules per story. Each module had have a 10-inch Hamamatsu PMT inside, and this is still in operation. KM3net ARCA will replace Antares when it is finally constructed. Now it's only at the first stages of its construction. There is a couple of strings which already deploy and working. It is located 100 kilometers offshore Sicily in Italy at the depth of 3,400 meters. It will be 2 blocks of 115 vertical strings each, with 18 digital optical modules on each string, And this optical module is a bit special because it has, instead of one big photomultiplier, it has 31 small photomultiplier. And this provides some advantages. This module is much more sensitive than a traditional module, almost 3 times. So it basically replaces 3 optical modules of Antares just with one such module. It provides directional information about the direction from which a photon arrives. So this helps with the reconstruction of events. And it's fully digital, and it also provides better counting of photons, and which helps with energy resolution. Vertical spacing between optical modules is 36 meters. 9 meters here is a typo. So 36 meters vertical spacing and 90 meters between strings. And as I said, this is under construction as the first stages of construction. So now let's go through some results, mainly by IceCube. On this slide, you can see the picture from a recent publication about the diffuse flux of astrophysical neutrinos. Here in black, you can see the data. Then the field histograms are for the background, mainly from atmospheric neutrinos. And as you see, the measured neutrino spectrum is higher than the background at high energies. And this is now interpreted as a presence of astrophysical diffuse neutrino flux, which is fitted here and is shown by a red curve. So as you see, at energies above 20 TeV or so, this astrophysical flux actually dominates over the atmospheric background. At least in this cascade analysis, the situation is a bit different in the track analysis. But here with cascades, basically you are completely dominated by astrophysical flux at above certain energy. And at energies of about 100 TeV and above, basically almost every event is astrophysical. So this is now a well-established flux. The individual events in this flux come from all over the sky. There is no real clustering of events. Therefore, only upper limits are set on individual sources. But before we go to point sources, here are some more pictures about the diffuse flux. Here on the left is shown a plot showing 2 different measurements of the diffuse flux and using 2 different analyses. Hesse is a high energy starting event. This is mainly cascade events starting inside the detector. And this is in purple, and in red is track analysis, mainly sensitive to muon neutrino. So you see they give slightly different fluxes and spectral indices, but overall quite reasonably consistent with each other. There are many measurements like this with different types of analysis. There's also an analysis by Antares. Unfortunately, because Antares is so small, it only observes diffuse flux at less than 2 sigma statistical significance. Nevertheless, they can fit this excess with a spectral model, and this is shown in red on the right plot. And this is consistent with IceCube results. So as I said, there's no clustering on the sky for these events. There's no obvious clustering. So only upper limits exist on individual sources. Here on this slide shown is upper limit plot for a list of candidate sources. These are black points or red points. Black points are for an assumption of E2-3 spectrum, and red is for an assumption of E2-2 spectrum. And this is shown as function of declination of the x-axis. As you see, ice cube is mainly sensitive to the sources in the northern sky, and so in the southern sky is much less covered by ice cube, and this is where additional neutrino telescopes are necessary, such as Antares or KM3net and Baikal. You can see here also the Antares sensitivity curves, which are shown in black, and you see even Antares, even though it's 100 times, almost 100 times smaller than ice cube, for some assumption of the spectrum, it's actually compatible in sensitivity to ice cube in this northern sky, sorry, southern sky. So here only four candidate sources appear a bit special, some excesses. The combined excess is slightly above 3 sigma, which is already interesting. So this is an evidence of some non-uniformity, but none of these sources is above 3 sigma individually. The strongest source is actually a galaxy, an active galaxy of, I think, a non-blazar type, NGC 1068. Anyway, that's an interesting candidate. Then there are also the multi-messenger studies where you look not only at the clustering on the sky, but also temporal coincidence or coincidence in space on the sky with some event or object seen in other wavelengths, like in gamma rays or other wavelengths. And so this is an event which is historic for the neutrino astronomy. It's a neutrino with a track-like neutrino with an energy of nearly 300 TeV. And this was observed in September 2017 by IceCube. An alert about this event was sent to many telescopes. Many telescopes have followed it. And actually, a coincident or some flaring event, roughly coincidence with this event, was observed by Fermi in the GeV band and by MAGIC at energies above 100 GeV. These are high energy or very, very high energy gamma rays. And this is observed at the location of TXS 0546, which is an active galaxy. So from here, it was concluded that there's probably some association between this neutrino event and this flare of this particular source. This coincidence could in principle be accidental, but then when IceCube looked at historic light curve of this source, they actually found an almost 4 sigma excess in the data from 2015. And so when taken together, this fact of coincident observation with a gamma ray flare and also this 3.7 sigma excess, this actually looks like quite a convincing source of high energy neutrinos. And of course, there's some spectral fit, which is shown on the left bottom here, trying to estimate what the spectral index and flux of this source is, and then what the location of this source. And it's, as I said, it's consistent with the location of this AGN. Now let's get to Baikal. Here is a picture of how the Baikal gigaton volume detector, or GVD, is planned to look. It consists of many clusters. Each cluster is an independent, basically an independent neutrino detector. And then you collect the data from these clusters on shore and search for your neutrinos. Currently, it's a collaboration of 10 institutes from 5 countries. about 70 collaboration members. It's actually a very small collaboration compared to IceCube or Games3Net. So so sometimes we have to take compromises where to put our manpower. And so far, our main priority has been the construction of the telescope. Here's a site of Baikal GVD. It's located at Lake Baikal, just nearly 4 kilometers away from shore. At this location, the lake bed is very flat, with only a couple of meters, plus minus a couple of meters deviations from flatness. The water is transparent to 22 meters in absorption and even longer for scattering. And in winter, there's a ice cover or nearly 1 meter thick ice on which you can drive and put your equipment, which is very convenient for the deployment of this installation.
Excuse me, Dmitry, you have 5 minutes, please speed up.
Yeah, okay. So so here is how this Baikal GVD looks. The cluster has 8 strings, and each string has 36 optical modules. The optical module includes a 10-inch Hamamatsu photomultiplier tube and some calibration equipment like LED. Additionally, you have LED beacons located along the strings. Also, some laser beacons, just a few for the whole array. And these beacons can illuminate basically the whole cluster. And with several beacons, you can illuminate the whole detector, somehow mimicking the high energy neutrinos. And we also have hydrophones for acoustic positioning. This provides calibration of timing calibration of 2 nanosecond accuracy and 20 centimeter precision for positioning. In spite of harsh weather conditions, ice conditions, we managed to deploy actually the 2 new clusters last winter. And so currently we have 7 clusters, and the combined volume occupied by these clusters is about 1/3 of the cubic kilometer. So far, we're moving through this deployment schedule just as planned, and we plan to build at least 15 clusters. So at least 8 more to go. Some first result from the track analysis. Currently, we have just a simple track fit with a chi-square-like function. Likelihood fit is still in development. From this simple fast fit, we get distribution of events like shown here on the right. This is before any cut on the zenith angle or even some quality cuts. You can see that we can roughly reproduce the data with our Monte Carlo. So this is good. Then on the left bottom plot, you can see how we select our neutrinos in this analysis. So we make a cut on the zenith angle, selecting only outgoing events, and then on the fit quality, and then we get a very clean neutrino sample apparently. This is what we expect from Monte Carlo, and indeed we see that once you do all these cuts, we observe 57 events, while expected is 54 events. This is what's shown here is the data from 2019 with 300 days of single cluster lifetime. This is single cluster analysis. The combination of data from different cluster clusters is still in preparation, has not been released yet for public. So, but at least at this point, it looks like we can observe atmospheric neutrinos and get rid of the atmospheric muon background, and everything looks like predicted by Monte Carlo. Here are some candidate events from this analysis. Typically, you have two strings on a cluster here. These are actually 4 separate events, each seen on its own cluster, and this is how they look. You can see the color shows the time. From red to blue is from early to late. You can see that these events come from below. For the cascade analysis, we expect, as I said, an effective volume of about 1/3 cubic kilometer with a threshold of about few TeV for this analysis of cascades. And the majority of events are around 30 TeV from atmospheric neutrinos. Basically, the median energy is probably about 30 TeV. And from astrophysics, we expect to be able to see astrophysics above 50 TeV or so. That astrophysics should dominate, and at above 100 TeV, mostly we should see astrophysics neutrinos. And in total, we expect about 4 events per year for a 7 cluster detector from astrophysics. So here's some details on the analysis. I think I don't have the time to go through the details. But what's the message here is that we are looking for these events, and with tight enough cut on the energy, and also if you select zenith angle not affected by the background, here we don't have a good estimate for the background yet, so it's not shown here. Anyway, we can see some of the events which look like they should be astrophysical origin, particularly one upgoing event with energy of about 91 TeV. And by the way, the angular resolution in this analysis is expected to be about 3 degrees. So here is an example of this event display of this event, which is so far our best candidate for an astrophysical neutrino. It has a 91 TeV energy, placing it in the energy range dominated by astrophysical neutrinos. It happened, the vertex, the interaction happened inside the GVD cluster, which makes reconstruction highly reliable and excludes the atmospheric muon origin or any other background origin. And the zenith angle is about 19 degrees from below horizon, which is also perfectly good angle for astrophysical neutrino of this energy. So this is likely an astrophysical neutrino from the diffuse flux. And this brings me to my conclusion. Many discoveries already were made in this field, in particular the diffuse neutrino flux seen by IceCube and the TXS0546 seen by IceCube. Now this needs to be complemented by detectors in the northern hemisphere, and currently Baikal GVD is the largest neutrino telescope in the northern hemisphere, and it started to deliver data with atmospheric neutrinos reliably seen, and also some first astrophysical neutrino candidates available. Thank you for your attention.
Thank you very much, Dmitry, for a very nice talk. We have time only for one question, I'm afraid. No questions? Okay, if not, let's go to the next talk by Dave Besson. Radio wave detection of neutrinos, please. 25 minutes.
Okay, thank you. So I'm going to talk about radio wave detection of neutrinos. This has been very nicely introduced by Dimitri in the previous talk. I'll mention that what we're specifically targeting, so Dimitri mentioned that they target the interval of maybe TeV to going up to PeV neutrinos. What we're interested in is in particular cosmogenic neutrinos. So these are neutrinos that are produced via the so-called GZK effect, where an ultra-high energy proton interacts with a cosmic microwave background photon. And ultimately what that leads to are muon neutrinos and electron neutrinos that have a typical energy of around 10 to the 17th electron volts. So we're probably about a factor of 3 or 4 orders of magnitude higher than what BICAL, for instance, is targeting. What's shown in this plot is basically the horizon for various cosmic ray tracers. So for instance, a proton has an observable distance at an energy of about 10 to the 20th electron volts and higher, of about 10 megaparsecs, which places it at the limit of the local galactic group. And again, this is precisely that GZK effect, which ultimately leads to the neutrinos that we're most particularly interested in. So what are the strategies for actually detecting these very ultra high energy neutrinos? What we're going to do is we're going to use the same Cherenkov technique that Dimitri just very nicely outlined, but we're actually going to use, instead of detecting Cherenkov photons with Hamamatsu photomultiplier tubes, we're actually detecting Cherenkov photons in the radio regime. So the schemes, the various schemes that I'm going to focus on here are schemes where there's a neutrino, for instance, that interacts in an ice target, not a water target. Remember that since we're going to use radio waves, we need a very radio transparent medium, and that excludes, for instance, salt water, and it also excludes, unfortunately, even fresh water because of the high dielectric constant. So, you're looking for a neutrino. It interacts in ice, and you can imagine 3 different strategies to detect that neutrino detecting in ice. You can either have a so-called synoptic strategy, where you place your radio payload above the surface of the ice and you scan down. That has the advantage of a large scanning volume, but you're very far away from the vertex. You can imagine putting radio receivers into the ice. You drill holes and you bury radio receivers, and that's the strategy followed by the ARA experiment. Or you can imagine a strategy where you actually put radio receivers on the surface of the ice. And in that case, for instance, if your ice is sitting over a seawater substrate, you can imagine looking for signals from a neutrino interaction which reflect off the seawater substrate and then back up to your receiver array. And that's the strategy which has been followed by the Ariane experiment. So here, here is a summary of the various experiments which strive to detect neutrinos. The first 5 of these are experiments which use an ice target. I'm going to talk a little bit more in detail about the RET experiment, which uses, instead of detecting Cherenkov radiation, actually uses a radar technique to sound the shower produced by an interacting neutrino. Beacon and Torogi M, these are experiments which actually scan down from a mountaintop, and it's looking for radio signals that are produced, for instance, from a tau neutrino, from a tau shower, or a tau meson or tau lepton decay, which is produced by a tau neutrino. These are respectively, there's a prototype in California for Beacon, and there's a prototype in Antarctica for Torogi. I just mentioned them here for completeness, as well as the ERA and Grand 200X, 200K experiment. And these are ERA and Grand 200K are looking for radio signals produced by a neutrino which interacts in the atmosphere, but at a very glancing angle. So you can look for Earth skimming radio signals. Owing to time limitations, I'm going to focus on the in-ice target experiments, namely the first 3 of those enumerated above. And I'll mention this is an idea that originated with Markov and Zhelyeznik at INR Moscow. Okay, so the Ascarian radio array is the first of the in-ice experiments that I'm going to quickly mention. So the idea again is that you have a neutrino, it interacts in ice, and in principle, in fact, there are 2 possible ray solutions that will propagate from the source to your receiver. There's a so-called direct solution, and there's also a refracted solution. And the fact that you have 2 signals that arrive at your detector separated by something like 100 to 200 nanoseconds is a very powerful and sort of irrefutable signature of an in-ice neutrino interaction. So most of the backgrounds are, for instance, coming from the surface. But if you see this double pulse signature, it immediately tells you that what you're seeing is an in-ice neutrino interaction. On right is shown the station detail, showing the radio receivers buried at a depth of about 200 meters or so. And here are the flux limits that ARA has been able to produce from their most recent publication. What's shown in black are the flux limits. What's important, I think, is that the shadowed band shows or indicates to you what the theoretical prediction is. So you see that even with the current experimentation, we're still about a factor of an order of magnitude away from the theoretical prediction. This can be improved and will be improved by looking at more data. This uses only about 10% of the available ARA data set, and also the lifetime of ARA will be extended by about another factor of 2 over the next 3 or 4 years. Okay, the other another experiment that I mentioned was the surface strategy. So here you put antennas very close to the surface, and again, you can measure, in principle, a series of different sources. You can measure neutrinos interacting in the ice. You can measure cosmic rays that are produced by, you can measure air showers produced by cosmic rays interacting in the atmosphere. And you can also measure radio signals produced by decaying tau leptons that are the result of tau neutrinos interacting in rock from a nearby mountain. And to date, the Ariane experiment has actually measured cosmic rays, although it has not measured any neutrinos. As a proof or a demonstration of performance, what they've done is they have measured their polarization sensitivity. So you need polarization information to reconstruct the Cherenkov cone. You need the, if you like, the theta and phi components of the Cherenkov cone to measure the actual neutrino geometry and trace that to a point in the sky. The angular resolution on a neutrino interaction. So if you're trying to measure, for instance, the angular resolution relative to a source, that angular resolution is measured at about a degree in both the elevation as well as azimuthal planes. The polarization measurement relative to measurements made in the lab is good to about a few degrees, which is quite good if you're trying to actually reconstruct the incident neutrino direction. Okay, the final strategy that I'll mention again is the so-called synoptic strategy, which to some extent has generated the most interest of late for reasons which I'll detail in a second. Here you take a radio receiver array, you put it up on a balloon, and again, you're sensitive in principle to air showers that are produced by ultra high energy cosmic rays. There you get radio signals, so-called geomagnetic signals that will propagate down to the surface, and then they will reflect back up to the gondola. When they reflect on the Earth's surface, on the ice surface, that signal should undergo an inversion of its polarity, which turns out to be very important. Signals coming up from the ice, for instance, from a tau neutrino, those will suffer no such inversion, and there you get a direct signal from an in-ice interaction of a neutrino. And in addition, there's the third class of event where there are so-called direct ultra-high energy cosmic rays, which will interact at glancing angles, and those produce direct radio signals. Notice that the radio signals produced by direct UHECR have an inverted polarity, opposite polarity relative to reflected UHECR. Again, in the second case, there's an inversion due to the effect of the ice having a higher index of refraction of air. Okay, so here again is a sort of a summary of the different signal types for Earth skimming neutrinos. For instance, you have an expected polarity that looks as shown in the figure on the left. And for a reflected cosmic ray signal, you have this inverted polarity, and the difference between these two is clearly obvious. Okay, so the ANITA experiment, again, is sensitive to these various types of signals, and a picture of the balloon itself as it's being filled for operation is shown in this slide. Here you see the Mylar balloon itself being filled with helium prior to launch, and what's shown in the lower left is the gondola. So this is actually a picture of this instrument. So the instrument consists of high resolution quad ridge horn antennas. Everything, of course, is solar powered. The total weight budget turns out to be about 600 kilograms or so. And again, this is another picture. This is the first launch of ANITA, and you can see the gondola at the very bottom and the balloon bringing it aloft. By the time the balloon gets to float altitude, which is about 38 kilometers, the balloon is inflated to something like the size of the Rose Bowl or Luzhniki if you're in Moscow. Okay, there have been actually now 5 different ANITA flights. There was the initial prototype, then ANITA 1 in 2006, 2007. And as time goes on, you can sort of see how the payload gets increasingly complex. The most recent flight of ANITA, ANITA 4, happened in 2016. And the most recent physics results to emerge from ANITA 4 were just released in the last couple of months, and I'll talk about those in a second. So perhaps the most interesting thing that has been generated by the ANITA flights is illustrated here. So what's shown here are a series of waveform captures. And what you see here are, for instance, in the upper left, this is a standard ultra high energy cosmic ray signal. It shows the polarity expected for a reflected signal. These are so-called direct ultra high energy cosmic rays. It also shows the same polarity, predominantly negative, expected for a signal which is Earth skimming but does not reflect off the Earth's surface. So this is a standard reflection. This is Earth skimming. They all have the same polarity. In the lower right is a signal which has about the same upcoming elevation angle as the standard ultra high energy cosmic ray at this sort of elevation angle. However, it has clearly inverted polarity. And there are a couple of events that have been observed of this type in the ANITA data set, and these are the so-called anomalous or mystery events. So the question is, why is it that this signal, which should have been reflected and inverted, has a polarity opposite to what most of the events, the pattern which is indicated by most of the events that ANITA observes. Now, a couple of caveats about this. The fact that the event is mysterious, in fact, there were 2 of these, one observed in the ANITA 1 flight and one observed in the ANITA 3 flight. The fact that they are mysterious is based on only one observable, namely polarity. It's just the fact that this signal is predominantly up and these signals are predominantly down in their polarity. So the first caveat is that, again, the mysteriousness is based on only one observable. Then the question is, well, maybe what you're seeing is really a neutrino, because then it would not have this inverted characteristic. But that possibility is ruled out by Earth absorption. at these sort of incident angles of 30 degrees, 35 degrees, the chord of Earth that the neutrino will go through is too large, so that, well, it's so large that the neutrino will have to have interacted before it can possibly produce a signal. The second caveat is that the waveforms that are shown are only shown after unfolding the Anita detector response. That is to say, they are so-called deconvolved. To that extent, all band-limited signals will look in principle identical. And the mystery events are otherwise indistinguishable from ultra-high energy cosmic rays in their FFT, etc. So, what you don't see are the original waveforms before deconvolution. This, of course, is the right thing to do, but you rely on that mathematical procedure to be correct. Then the other thing is that, of course, the Antarctic surface is not monolithic. There are ridges and crevasses, etc. And then also radio from ultra-high energy cosmic rays hitting the surface is also accompanied by so-called transition radiation. If the ultra-high energy cosmic ray core hits the surface, it will produce so-called transition radiation or stopping radiation. And as Hamlet said, there are more things in heaven and earth that are dreamed of in your philosophy. So those are the caveats to keep in mind. I'll mention that what we did, and I'll go through this quickly. So we were aware, for instance, of this problem. And what we did is we constructed an experiment called HiCal, which basically flew behind the Anita balloon, and it sent out a pinging signal that was measured both in terms of its direct path as well as its surface reflected path. So this is a way of trying to calibrate the effect of surface reflectivity. The azimuthal detector on HiCal was actually built at MEFI. And what we found is that if we were to make a plot of the surface reflectivity for Antarctica and compare that with the expectation from the well-known Fresnel coefficients, we got very good agreement between the expectation and our data. So that seems to exclude the possibility, or at least make less favorable or less probable the possibility that what we're seeing is in fact some surface reflection effect. Okay, so what are the other possibilities? People have looked at the possibility that that what might be happening is that when the surface, or sorry, when the current from the air shower core intercepts the surface, it produces this stopping radiation, and this stopping radiation produces a so-called transverse current, which generates an RF signal at the balloon. That possibility has not been excluded, and that remains a viable explanation and possible explanation for the Anita mystery events. There are other possibilities that have been offered. Before getting to that, let me mention the most recent result from Anita 4. So Anita 4 has now seen a total of 4 additional so-called mystery events with a total significance of 3.2 sigma, and this was just released actually within the last couple of months or so. So now the total tally of mystery events is 1 from Anita 1 from Anita 3, and now 4 more candidates from Anita 4. What is interesting is that the Anita 4 events, unlike Anita 1 and Anita 3, are almost at glancing angles. So they're very, very close to the horizon. Now, it's been suggested that these events might be the result, the mystery events might be the result of a so-called subsurface reflector, that you take a conventional ultra-high energy cosmic ray and you take radio from that ultra-high energy cosmic ray, and it's just reflecting off of not the surface, but a subsurface feature that has an index of refraction characteristic such that you don't get an inversion. We've actually modeled this, and this is the paper which offered that possibility. We've actually modeled this possibility using Anita and HiCal data. What's shown in the bottom is the expectation that you would expect to see if you had, for instance, initially a surface reflection and then a subsurface reflector you would see first an inverted echo and then a non-inverted echo. So this thing all the way on the right is what the authors are proposing Anita might be seeing. We did a statistical analysis. I don't have time to go into it, but I will say that we did a statistical analysis. Everything to the lower right is stuff that disfavors a subsurface reflector model and is consistent with just conventional physics. Everything up and to the left is our data that would favor the subsurface reflector model. So clearly, all our high cal data disfavors and would otherwise contradict the idea of a subsurface reflector model.
Excuse me,
Okay.
Dave, you have
Yeah.
5 minutes
Okay.
left.
Okay. All right. There's been suggestions that these events might be due to the triboelectric effect. Masha Mikhailova spoke about this on Tuesday. This has been observed, for instance, in the rice and ore experiments at the South Pole. However, that statistical analysis has not yet been conducted with the needed data. It appears from a first glance that the events that we've seen, the mystery events, are not due to a triboelectric effect. Okay, I'll finish by just mentioning an additional technology that might be used to detect ultra high energy showers, and this is this radar technique. So here, for instance, there was a test beam experiment at SLAC where you took a test beam that generated a shower. There was a transmitter, and the transmitter produced an echo off of the shower itself, and that echo was observed in the time domain. So what's shown here is the echo off the charged particles in the ultra high energy shower cascade. You can also represent that in a spectrogram. So this bright spot here corresponds to the time when the observed echo was brightest, and it also corresponds to the time when the shower development within the target in the test beam environment should have been fully mature. So we see very strong evidence for these echoes, and moving forward, there's actually an experiment which has been approved to deploy a prototype test, sort of a test bed experiment in Antarctica at Taylor Dome, and that will happen around 2023. Okay, so future experiments. Anita 4, the Anita series is done. There's just been a proposal submitted actually yesterday for the next generation of the synoptic balloon-borne strategy that's called PUEO. And that will reduce the trigger threshold from an SNR of 6 to SNR of 2. We expect an Antarctic flight of 2024. And again, I just mentioned the radar experiment, Taylor Dome, in 2024. All right, and I'll just close with one final slide. So where is everything going in the future? Well, there's basically one future direction, and that's the IceCube Gen 2 experiment. The IceCube Gen 2 experiment is a successor. Dimitri mentioned this. It's a successor to Gen 2, and it will have a coverage, at least in terms of the optical array, of about maybe, as you can sort of read off this slide, maybe 4 to 6 square kilometers. So this is the footprint of the current IceCube. Just to the left of it is the planned footprint of the IceCube Gen 2 optical array. And in addition, there is a very large scale radio array which is proposed. This is Gen 2 radio. This will be about a $50 to $60 million, maybe a $50 million endeavor. It is massive. It will include 800 ice holes drilled in the ice over a footprint of about 500 square kilometers. So the plan for Gen 2 radio is that it will be large enough so that by almost all models, it should be able to detect something like 10 cosmogenic neutrinos plus, that 10 number includes both cosmogenic neutrinos, and it should also have sensitivity to the very high end of the astrophysical neutrino spectrum as measured by IceCube Gen 2. That is to say, it should have a threshold that starts around 10 PeV, and it should extend all the way up into 10 and 100 eV and beyond. And I'll stop there and thank you for your attention.
Hey, thank you very much for this very nice talk. So we have time for questions now. Several questions. No questions.
I can ask one. So how deep do these holes need to be for the radio array?
So this is a question which is not simple to answer. So the upper 100 meters of the ice at the South Pole has not yet reached its asymptotic density. It's called Fern, and because of that, the horizon or the ray tracing is limited. So you do best when you deploy your hardware at a depth of, say, 200 meters. There, the ice has its maximum density, but above 200 meters, the ice has not yet reached its full density, and ray trajectories curve by Fermat's principle. So, so the best depth from a standpoint of visibility is to go down to 200 meters. However, the logistical impact of deploying, so much hardware, 800 holes to 200 meters is obviously much more substantial than deploying to 100 meters. So from a science standpoint, I think it's clear that you'd like to go down to 200 meters if possible. And certainly the drill we have can get us down that far. However, from a logistical standpoint and the impact that this will have overall on the operations at South Pole, it may be that we'll be limited to 100 meters, or in fact, it may even be the case that there'll be no holes and ultimately will be limited to a surface deployment. So in getting to that final answer, there's going to be a balance between the science drivers as well as just the logistical boundary conditions and restrictions within which the experiments are operating.
Thank you.
You're welcome.
Okay, so I see one question in chat. Can you see this question, Dave?
No, I can't.
So the question is from sorry if I pronounced not correctly, Mohammed Fu Hassan Sheikh. How do you differentiate between direct signal and in-ice signal if the polarity is the same?
How do you? Because yes, the polarity is the same, but our reconstruction, our angular reconstruction, is about 0.3 degrees. So we can clearly tell if a signal, we know the arrival direction very well, and we can tell whether or not the interaction happened, for instance, in the atmosphere, because the horizon relative to the balloon is at an elevation angle of about 6 degrees relative to the horizontal. So at an elevation of 38 kilometers, you look down, and the horizon is 6 degrees below horizontal. So anything above that, for instance, 5 degrees, as in the picture that I showed you before, we know is coming from a direct signal. Below that, it's coming from either a reflection or an upward coming neutrino. But ultimately, it's because the angular resolution is, like I said before, about 0.3 degrees.
Okay, more questions, comments? So if not, we should close the section, but please stay because it was announced in timetable that now it will be conference picture. I don't know how it will be done, but organizers will have announcement now, please.
Yes, so in 1-2 minutes we will start. Please enable your cameras. And meanwhile, I will tell a couple of words from the on behalf of the organizing committee. We would like to thank you for your participation, and the conference was very interesting. It is still ongoing. We will have several. We will have a plenary section, evening plenary. No, we will have a parallel section today, evening parallel section. But now I think we will. Sorry, please turn on your microphone. So I would like to thank you all and hope to see you on our next conferences. And I would like really to invite you to our next conferences. Okay, so please turn on your webcams if it is possible. We will try to make some photos, and we will try to make a collage out of these photos. And I hope that next year we will, or on the next conference, we can meet in person, not like this. I hope that these circumstances are exceptional. Okay, Peter. So.
Not yet. Just wait a couple of seconds.
Okay, so please remain your web cameras on, at least for 1 minute. Actually, there were a lot of interesting presentations and very exciting presentations from our invited speakers that inspired us, I think. And you will have a possibility later to see some videos, to see the video from the plenary sessions. So maybe it will be also useful for your students who cannot attend. It's really wonderful to see you all. Thank you, guys.
You know, it is hard to smile for so long time.
So thank you. I think I made enough photos. Thank you all. See you.
Thank you. And see you. Stay healthy.
Thanks, everybody.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you for the conference.
Thank you. Thank you.
Bye-bye.
Thank you. Bye.
Thank you. See you.
Thanks, organizers. Thank you.
Many thanks.
Thank you for organizers.
Thank you. Thank you.
Thank you for the conference.
Thank you, organizer.
Bye-bye.
Thank you. Bye.
Thank you.
See you.
Thanks, organizers. Thank you.
Thanks so much.
All of you, thank you, sir. Thank you, madam.
Тебя или меня?
Thank you.
А я вот на большом экране был и не могу убрать. Вот. Да, я понял, что уже все говорились. Спасибо, до свидания.
Thanks a lot. Goodbye.
Давай, давай.
We disconnected.
Хорошо, да.